I hope you guys don't have a good spring break. Are back, with the batteries charged and refreshed, full of energy for the second part of the semester. So the midterm results are in. Uh, I think you guys got the corrections by email from the TA. Is that right? Okay. And I'm going to give you your graded midterms at the end of the lecture. Okay. So you can take them with you. So here's a summary of the scores. The pretty broad range of scores going between 35 and 95. And the average is around 57. Okay, so I would say the midterm had two distinct parts. At least that's the idea I had in mind. So the first three problems were intended to be a little more, let's say, basic. So very much similar to ones we had done for the homeworks. And I expected most of you to do well for the first three problems. And most of you did quite well for problems 1 and 3. Some of you had problems with problem 2. I don't know exactly why, but things didn't go so well for problem 2. It went well for problems 1 and 3. But that was the idea. There was this first part. And then the second part was problems 4 and 5, which were a little more advanced, a little more out of the box in terms of being different from the homeworks. And you guys did all right in problem 4, and most of you struggled with problem 5. So, as I said, I'll give you the graded terms, midterms after the lecture. Look at them, go over the what you did and your scores. And those of you who feel that you may be falling behind the pack, please come to see me if you want next week during office hours. Or if you can't make it during office hours, send me an email. I will try to find another arrangement so we can talk. So by all means, even if you did well, I mean, whatever concern you may have at this point, come to see me or send me an email, and we'll look at what you did and where you may be falling behind if you are, etc. Okay. So I thought that maybe before starting with the lecture, we can go over the solutions to the homework, to the midterm. Would you guys think that's a good use of time to quickly look at them? So if you have any burning questions, or something that's not clear even after seeing the solutions, maybe we can sort it out. Okay, so here's the midterm, and here are the solutions. And I hope that's visible. Yeah, I think that's right. Okay, so let's quickly go over them. The first problem, which was pretty similar to things you had done for the homeworks, right? So you should have done well here. We have a cell of 1 kilometer size, of a certain power, 0.7 watts, and we have path loss following the usual model with slope power to the -3 and an intercept k, which is equal to 1. So it just boils down to the k with a cube of the distance. And we have the bandwidth. And we have the noise spectral density. Okay, so we have all that stuff. And we know the shadow fading is the usual log normal with 8 dB standard deviation. Okay, so these are pretty much usual parameters that should sound familiar. There is no multipath fading. There is only shadow fading. And you're given an approximation for the Q function if you want to use it. So there is only one question here. Find the percentage of locations within the cell where the channel capacity is greater than 300 kilobits per second. Okay? And there are formulas that you were given to find the coverage in a cell. And those formulas are in terms of power, right? So the first thing we have to do here is map capacities into powers. Okay, so we're given the capacity that we want. We're given the bandwidth. So how much power do we need? Okay, so we wanted the capacity of 300 kilobits per second. So it's 300 times 10 to the 3. And the bandwidth is 100 times 10 to the 3, 100 kilohertz. So that goes in front of the log. And then we have the log to the base 2 of 1 plus P min, which is what we're trying to find, divided by the noise spectral density times the noise bandwidth. So this is the noise power, N0 times B. Okay? So out of this equation, we have everything, and all we have to do is clear P min. Okay, we clear P min, and it comes out. Here it comes out in linear scale. We convert it to dBm, and if you want to, you don't really have to. And it boils down to minus 61.54 dBm. Okay, so that was what you had to do here. The first step was use the capacity and the bandwidth to find P min. All right. Now, once you have P min, how do you proceed? Okay, now you want to find PR. All right. Remember, PR bar is the average power at the edge of the cell. Okay, and it's just PT divided by the cube of the cell size, right? Because you have the power, the path loss goes with the cube of the distance, and the intercept is equal to 1. So the received power at the edge of the cell is going to be given by this ratio. And we have PT, which is 0.7 watts. We have the cell size, which is 1,000 meters, right? So we plug this here, and out comes the PR, which in dBm is again minus 61.54, right? So this was chosen carefully, so the problem would be even easy. I mean, you could solve the problem with these two quantities being different, but it simplifies even further when they're equal, right? When they're equal, and here you can refer to somewhere in chapter 2, we have the formulas for cell coverage as in the basis of power. So formula 2.60 is the one for when P min and PR are different. And in the case they're equal, it simplifies to formula 2.61, which is reproduced here for you, right? This is the formula. Let me use the pointer. So this is the formula for the coverage in the special case that PR and P min are equal. So all we need is to find this parameter B, which we can do up here, because you have all the quantities that are involved. Okay. So you compute P, this 8 is the shadow fading standard deviation, etc. And you just plug B into this formula, and out comes assuming you have the Q function, you can get the exact number, which is 0.73. And if you use the approximation given to you, you get 0.82, which is a little higher. And that's it. Okay, that's the end of the first problem. So most of you did well here. Some of you got very confused and mixed up. So there were two typical errors here. One is to mix up the gammas, gamma being the SNR and gamma being the exponent of the path loss. So I told you guys in class, be careful, these two gammas have different meanings. We use them the same variable. And then the most typical mistake was to use formulas for coverage at a certain distance as opposed to coverage over the cell. So you guys use formulas from section 2.9 as opposed to section 2.10. Some of you did. And got coverage at a particular distance as opposed to getting coverage over the cell of a certain size. But other than that, most of you did fine here. Questions? Okay, everything's clear? Okay. All right, so let's look at the second problem. Oops. Second problem, we have the usual discrete fading channel with 4 states. And you guys had worked some of these in class. So it was entirely similar. I'm using the formulation. So you have 4 possible gammas, SNRs, 5 dB, 10, 15, 20. And the corresponding probabilities. All right, so we have 2 questions here. The first is find the capacity and the optimum power allocation with both transmit and receive CSI. So we have to find the optimum water filling. So we need the gamma 0, right? So what we can do first is convert the 4 gammas into linear scale. So the dBs into linear scale. We get 3.16, that's 5 dB. 10 is 10 dB. 31.6, and 20 dB is 100. And we just pose the usual formula that's in the textbook also to find gamma 0 for discrete channels. All right, so you have it in section 4.2.4 of the textbook. Actually, formula 4.17, right? So you just have this, the reciprocal of each gamma times its probability. And we have 1 over gamma 0. So you have this equation equal to 1. And we have to clear gamma 0. And we just work it out, trivial algebra, and we get 0.86. Okay? So using this gamma 0, we can find the capacity divided by the bandwidth, and we just, again, add up all these terms, and we get 3.87. Okay? So this is pretty much a repetition of things you had been doing for the homeworks. That's the first question. Question B was to find the same C over B when we're using truncated channel inversion. So here we had to find, so next page. Okay. So we have to find again the right cutoff. We have to find the cutoff using this, remember this expectation E sub 0 formula, right? So remember that when we have these discrete channels, right, usually we want to find the cutoff at one of the transitions, at one of the gammas, exactly, right? So we can try, we have 4 possible gammas. We can start with the first one, 3.16. And if we choose it at or below 3.16, we have that there's no outage. So all the channels, all the 4 gammas are taken into account. So we have these expectations sub gamma 0 is giving us 0.15, more or less. And the corresponding capacity is giving us 2.9. Okay, remember that all we have to do is compute log 2 of 1 plus the reciprocal of this gamma, of this expected sub gamma 0. Okay. We can then choose a higher gamma 0. So we can go to somewhere between 3.16 and 10. In this case, the lowest gamma, 3.16, is going to be an outage. So we discard it. We have three left to play with. So we recompute it only with the top 3. And we get a smaller value here, of course. And we get a higher capacity in this case. C over B is 3.1, so it's gotten better. We can go up another notch and now say, okay, say gamma 0 is between 10 and 31.6. Then we only have 2 of the gammas that become active. The other 2 are in outage. We recompute everything and we get even a smaller value here. And now C over B falls again to 2.77. And we could do, I didn't do here, but we can do the final one, assuming that gamma 0 is between 31.6 and 100. And you will get an even lower value, right? So you do the 4, and you find that the best one is this 3.1, which is the answer. And it corresponds to leaving the smallest gamma in outage and finding a threshold that's between 3.16 and 10. Okay? And there's a second part of the question that says, what is the receive SNR when the system is not in outage? And it's just this sigma, but you already computed actually, because this sigma is 1 over, it's essentially what you put inside the log, this thing over here. And for the one that came out the winner is 1 over 0.028, and it's 31.7, which in dB is 15.5. And that's it. Problem number 2. Questions? All right. You guys are very quiet today. Okay. Number 3. So we're given a channel impulse response, C of tau comma t, which is a delta. Yes. Go ahead. You're asking about the previous question, problem, right? Okay, sorry, let me go back. Okay, so the question is, shouldn't the C over B always improve with gamma 0, right? No, it doesn't, right? This is, you see here that it doesn't, right? There is an optimum, and it can be anywhere. It really depends on the gammas and the probabilities. So otherwise, it would be trivial, right? The problem would be trivial. If you always increase, then you should always pick it equal to the largest gamma or something. So it depends. Usually it'll be somewhere in the middle. And in this case, for example, it pays off to drop the smallest gamma and leave it as an outage and just guarantee service on the other 3 gammas. It just happens because the probability of that gamma is probably quite small. Let's see. Well, 0.4, so it's still significant. But somehow it pays off to have 40% outages. And remember, this is for the case that you're using this truncated inversion. This is not optimal. Remember that the optimum is to do the water filling that we did in the part A. But this is the simplest policy. And what happens is that the smallest gamma is so small that it takes a lot of power to invert it. So as it turns out, it pays off to just it does it as an outage and just invert the other three. So it's only the numbers in this case. No? Question? No. Okay. Other questions about problem 2? Or? Okay, let's go on with 3. So here we have this impulse response, which is three impulses. One at 0, one at a delay of 10 microseconds, and one at a delay of 40 microseconds with weights 1/2. So the first question is very easy, right? Is this channel time varying or time invariant, right? I hope all of you did this correct. I didn't check, but I think most of you did, right? So since there's no dependence on t, right, that means that it's time invariant, right? That's it. So you don't have to hesitate. If you're sure, you should be sure of certain concepts, right? If there is no t here, then this does not depend on t, so it's time invariant. And end of question. Now, let's say that we send a signal that is 2 pulses, rectangular pulses, of duration t sub s, and amplitude 1. We send 2 pulses, just one after the other. What do we get at the output? Well, okay, we have 3 impulses, right? Each one is going to give us the 2 pulses with some delay, so we're going to get 6 pulses, right? We're going to get 2 pulses with the same amplitude that they came in, and then 2 more pulses delayed by 10 microseconds and divided by 2, and 2 more pulses further delayed by 40 microseconds and also divided by 2. Now, we have to see how this looks like, right? And now that's where the length of the pulses becomes critical. So that's why there are 2 sections here. In the first section, the pulses are 20 microseconds. So we have 2 pulses of 20, and then with a delay of 10, we have 2 more pulses of 20, and then with a delay of 40, 2 more pulses of 20. So these pulses end up overlapping. And if you draw these things together, and I'm not a great drawer, but I did my best here, it should look like something like this. Set comes in, and so the other 2 come in. In fact, let's go to the next picture. Let's do the second part first, because it's easier. This one is easy, right? Here the pulses are short, so there's no overlapping. We have 2 pulses. Okay, this is 2 pulses, one after the other. So you can imagine there is a division in the middle. It's 1, and then here the guys are 40 microseconds. Okay, now if you imagine this is getting wider and wider, at some point they start running into each other and adding up. And when you extend them to 20 microseconds, this is the picture that comes out. Okay, so that's about it. And then the point was to see whether there was ISI or not. Okay, and clearly here there is. Now this is a mess. So there is big time ISI here. So you need an equalizer to correct for this. Instead, this guy doesn't have any ISI, right? So the pulses do not overlap with their delayed replicas. And that's it. And somehow you guys had a lot of difficulties with this problem, which I don't quite understand. But any questions, comments? Why you guys are confused? Anybody wants to say something? Is it clear now or not? Nobody? Okay. Moving on. Problem 4. Okay, here you guys, most of you got stuck in the same place. Some of you did do this problem correctly, so it was doable. Here we have a channel that's now continuous as opposed to discrete. And this case. It's now being continuous. You have to solve it differently. So the first question is to find the averages in R. Okay, this one is very easy, right? So we are told that the fading distribution looks like this. It's okay, let's see. So this is gamma, and this is a PDF of gamma probability. And we're told that it goes between 1 and 11. And it's uniform. Okay, so that means that the probability is constant between 1 and 11, and is 0 outside. Okay, so the gamma never goes above 1, never goes below 1. Sorry, never goes above 11, never goes below 1. And it takes values between 1 and 11 with a uniform probability. Now, which is the probability? This probability level. You guys know that the integration of a PDF has to be equal to 1. Because something has to happen, right? So the probability has to add up to 1. So the area of this rectangle has to be equal to 1. So if the base is 10, the height has to be 1 over 10, right? So that the area is equal to 1. Okay. So now this is the fading distribution. So what's the average gamma? Well, it's just by, I mean, you can do integration if you want, but by inspection, the average gamma is 6, right? By symmetry. If you want to do it properly, you can integrate from minus infinity to infinity gamma times P of gamma. Right? This is how you compute an average. And this is equal to the integration from 1 to 11 of gamma times 1 over 10. Okay. And if you solve this integration, it's going to give you 6. So that's the first part. Now, what's the capacity of an unfaded channel with these averages in R? Well, it's just log 2 of 1 plus 6, which is 2.81. Okay, that's it. That's the first part. Questions here? Does anybody see these, or does anybody not see this? Okay, so let's go to the second part. The second part says, suppose we have both transmitter and receiver have CSI. Find the optimum C over B and the optimum power allocation, which is the water filling. Okay, so it's the same thing we did for problem 2, except now it's continuous. Okay, so we have a similar formula, which is equation 4.15 is what we have to use to find gamma sub 0. So let me write it down. We have that the integration from gamma 0 to infinity of 1 over gamma 0 minus 1 over gamma times P of gamma. You have this equation from which you have to find gamma 0. And this P gamma is the one we just saw. It's the uniform between 1 and 11. Okay? So now, most of you did the following. Okay, this is integral from gamma 0 to infinity of 1 over gamma 0 minus 1 over gamma times 1 over 10 d gamma. Most of you did this, actually. Most of you did almost fine here. Integrated between gamma 0 and 11. The problem is that we don't know if gamma 0 is above or below 1, right? And that makes a difference. Because if it's below 1, then what happens? Because remember that let me draw again the picture. Okay, so we don't know if gamma 0 is between 0 and 1 or is above 1, right? If it's above 1, then that's correct, right? But if it's below 1, the integration has to start at 1, right? Because the PDF doesn't fall below 1, it's 0, right? So the right formulation is to have in the integration an lower limit to have at this point the maximum of 1 and gamma 0, whichever is biggest, which we don't know yet. Or if you want, you can just try both of them and see what happens, right? But the right formulation is to say at this point, okay, I don't know which one is biggest because I haven't determined gamma 0 yet. So whichever is biggest is going to go here. Okay? Now you can carry on the integration. It's a very easy integration, right? This is just a constant, and this is just 1 over x. It's just a log. And you can actually, you can retain these max in the integration limits, and you can actually work it out. Most of you didn't do this and just kept gamma 0 here. Now, and you get a nonlinear equation that you cannot solve. Now, the right thing to do here is say, okay, gamma 0 can be smaller than 1 or bigger than 1. So let's try both cases, right? If it's bigger than 1, you get a messy equation that you cannot solve. If it's smaller than 1, you get a very simple equation that you can solve trivially and gives you that gamma 0 is 0.81, which verifies the assumption that it's smaller than 1, and so this is the correct answer. Okay? The problem is that most of you just formulated the integration in this way and just assumed the integration starts at gamma 0, which gives you this nasty equation that you couldn't solve, of course. So once you have gamma 0, and even if you didn't get gamma 0, you know, I give you credit for if you did the rest, okay, I give you partial credit. But some of you did get the answer, so thumbs up to those. And if you do find gamma 0, then you just plug it into the other formula, which is 4.13, which gives you the capacity, okay? And by the way, there's a typo here in the corrections, guys. So here, the 0.81 should not be here, so if you want, you can correct it. And the correct answer is this number times 0.81, which is around 2.6. So your gradings have been done with the correct version. So we just saw this after we scanned it. So keep this in mind that the correct answer is 2.60 something, and that the corrections have taken that into account. So that was my mistake here. Okay, and the final part of the question is, what's the probability that that gamma is below gamma 0? And it's actually 0, right? Because the fading never falls below 1, and gamma 0 is 0.8, so it never falls below it. So that's part B. Any questions here? Yes. Okay, so you're saying you integrate from 1, right? Is that what you're saying? Yes. From 1. And then you weight everything by the probability that, but you don't know that probability, right? Because you don't know gamma 0 at this point.
Well, I mean, based on the probability gamma plus the probability gamma 0 times.
Oh, I see. But then you're assuming a uniform probability, right? It's uniform between 1 and 11. So you're saying I'm not sure I'm following what you're doing. Is that what you did in your midterm, or?
I don't remember at all.
Ah, okay. No, okay, we can look at it at the. Let's look at it at the during the break, um, because I need to understand exactly what you're trying to do. So let's come back the break and we'll take a look. We'll see if it's right or not. Other questions about this part? Yes.
I think what the problem is that if we're going to integrate knowing that gamma 0 is less than 1, then we integrate from gamma 0 to 1, and the probability in that space is 0. So when we multiply it's 0. And then we do two integrals, one from gamma 0 to 1, and the other from 1 to 11. And we know the probability between 1 and 11, and the probability between gamma 0 and 1 is 0.
Between gamma 0 and 1 is 0.
This is one.
But what if gamma 0 was bigger than 1? That certainly works. That certainly works if gamma 0 is less than 1, which it was here, right? But it could have been otherwise, right? Gamma 0 could have been 2, for example, right? So then that's what I want to see if that works also in that case. So it certainly works. Gamma 0 is between 0 and 1, but if gamma 0 is bigger than 1, I'm not sure that works, because then you have a negative probability there. So I don't think it works in that case. So what happens is that if you did that in this case, you probably got the right answer, right? But you got lucky. Well, you got lucky in the sense that doing it this way, you're not going to get the right answer, although you do get it in this case, right? Now, if you convince me that you always get the right answer, I'll give you full credit. I don't think you do. When gamma 0 is bigger than 1, you get the negative.
That's why you get it.
Yeah. So, so we gave partial credit to this. So there are people that got the right answer with a procedure that was somewhat questionable, but you got some credit. Other questions in this part? Okay, so there's a third section here, part C, which says, let's see. Okay, now we use channel inversion again. So find C over B. Okay, so we have to compute this sigma, which is the expectation of 1 over gamma, to remember. And in this case, it's a very easy integral, right? It's just the integration of 1 over gamma times 1 over 10, and we integrate between 1 and 11. And it just comes down to this logarithm and outcome 0.24. Okay, so sigma is 1 over 0.24, which is just over 4. And then C over B is just the log 2 of 1 plus 1 over this, which is 2.36, whatever. Okay, so this part was pretty easy. Questions here? Okay, so let's go to problem 5, which most of you struggle with. Okay, so the question is, let's consider an unfaded channel. So we only have two quantities to play with, the bandwidth and the gamma, okay? So capacity is B times log 2 of 1 plus gamma, okay? So obviously, if we double B, we double the capacity. And in fact, the capacity is linear. It's linear in the bandwidth. Now, suppose that we don't have the luxury of doubling bandwidth, because bandwidth is very expensive. That is a fact. So power is cheaper. So let's say we just want to double the power. Well, that doesn't pay off. It doesn't pay so much because we have a logarithm in the middle. Okay, so logarithms, scale worse than linear. So we don't get as much return for doubling the power. Now, is there ever a condition under which we do get doubling, right? And so essentially, we have this, right? Okay, so we're going to try to double this guy. So are there any conditions under which this is going to double C? Well, the only things that come to mind here are, this is obviously not true for general gamma, right? Because, the log is not a linear function. So, multiplying by 2 the argument doesn't multiply by 2 the outcome, period. Yeah, if you square it. If you square it and you don't have this part here, then it works. But in general, it doesn't work. So it can only work in some limiting case, right? So for big gamma, for small gamma, those are the only two possibilities. So you can just try those out, right? For big gamma, you can just do it with a calculator and see that it's actually a very flat function. So it gets even worse. And for small gamma is when it works. So all you have to do is you can do it, with the calculator doing a few cases, and you could see that it grows linearly. Or you can just do a time or series expansion, which is what I had in the solutions, which is trivial in this case because the derivative of the log is trivial. So you do a time or series, and you get that C is approximately equal to B times gamma times log 2 of B. Okay, so for a small gamma, when gamma is small, this is the time or expansion, and you see that it becomes linear in B. So when you double, in gamma. So when you double gamma, you double C. Okay? It's approximate because here there's a second term which has a gamma square and stuff. But to first order, at lowest NR, and this is something that system designers exploit all the time. At lowest NR systems, the capacity is very power efficient. So you get the same return by doubling power, doubling bandwidth. At highest NR is the opposite is true. So that was the first part. Questions? Comments?
If the signal noise ratio is high, though, could you say, well, it's basically, if it's high, if it's much greater than 1, then it's basically the signal to noise ratio is the log, right?
Yeah.
So if
you
square the signal to noise ratio, then you'll be able to double the capacity.
Yes. So the question is, at highest NR, then this 1 plus essentially disappears. Then if you could square the power, you would double the capacity. Yeah, square the signal to noise, right. Definitely. But the question was about doubling the signal to noise, not squaring it.
Well, I thought it was doubling the half resolution.
No, but the question is there, okay, let's look at the phrasing. I'm sure it was clear, right? Oh, okay. Yeah, okay. So he says, suppose that with all the transmit power.
Yeah. So if you said that the transmit power is equal to basically P squared plus.
Yeah. So what you say is, okay, if I divide the noise somehow, for example, right, second square. Okay, that was not the intended question, but I see your point. So you took it this way. Okay, all right. So okay, let me look into that. So you answered a different question, not the one I intend to ask, but I'll take that into account. That's the way it's phrased. That's a plausible interpretation, even if it's not the one I meant, but it's a plausible interpretation. So if any of you all guys also had similar issues, please bring them up, bring them to my attention. Okay, if you answered, if you understood the question in a different way and answered that question, I'll give you credit for that to some extent. Okay. So come to see me in the break. Okay. Okay. Now the second part was asking, what's the largest increase we can obtain through doubling of PT? And here the wording was more specific, right? What's the largest possible value for this difference? C of 2 gamma minus C of gamma. Here, I think here there's no ambiguity. We have C of gamma is equal to log of 1 plus gamma. C of 2 gamma is equal to log of 1 plus 2 gamma. Okay, so C of 2 gamma minus C of gamma So as you know, the difference of two logs is the log of the ratio. So that's what we have, right? So when is this logarithm maximized? That's the question, right? And since the logarithm is a monotonic function, the maximum of the logarithm is obtained when the argument is maximized. Okay, it's an increasing function. So to maximize it, we can just maximize the argument. So when is this function maximized for which gamma? Well, here there are multiple procedures. You can do it the rigorous way. You can take a derivative and set it to 0. Or you can just take the calculator and punch a few numbers and see how it progresses. Or you can plot this function, which is probably the easiest way. That's what I did in the solutions. It's a very easy function to plot, just looking at its asymptotes and stuff. And it looks like this. Right? Starts at 1, and it asymptotes to 2. And so the limit is, the highest value is achieved when gamma goes to infinity. Okay, so it's monotonically increasing, it approaches 2. And so the answer is that you get the maximum return at high gamma, so when gamma is large. And that's the answer. Okay, so whichever way you phrase it, if it meant highest in R or large gamma, gamma bigger than 1, pt bigger than whatever, as long as you meant a large gamma, you got correct. And that's it. Questions about this point? All right. And now I'm sure you guys are all eager to start with new material. So we'll start chapter 5 of the textbook. And let's, before the break, review what we saw in the last lecture, and then we'll take it from there in the second half. Okay, so we spent some time talking a few weeks ago already about digital modulations. Let's review what we saw since it's been a while. Okay. So we talked a little bit about why systems are digital, what are the benefits of digitizing information, and why, for example, that we can actually compress it before transmission to squeeze out any redundancies. And then we defined modulation as the mapping of bits onto a transmit signal, and detection as the estimation of the original bits from the received signal. So those are the two tasks that we're going to concern ourselves with in the next 2 or 3 weeks. Modulation and detection of modulated signals. There are 2 main classes of modulation, linear and nonlinear. In linear modulation, we embed the data into the amplitude and or the phase of the signal. This form of modulation is spectrally efficient, so it's bandwidth efficient, but is more susceptible to noise, and it requires linear amplification, so it requires more expensive equipment, and the spectral efficiency comes at the expense of power inefficiency, because these amplifiers, these linear amplifiers, tend to be inefficient in the sense that they waste a lot of power in heat dissipation. Then there's the other class of modulation, which is the nonlinear modulation, which embeds the data into frequency of the signal. These modulations are spectrally less efficient, but much more robust to noise and interference. And they can use nonlinear amplification, which is cheaper, and it wastes much less power in heat dissipation. Okay? So I think I told you that GSM systems use nonlinear modulation. So providers such as T-Mobile and Singular use nonlinear modulation, and CDMA uses linear modulation. So Verizon, for example. Okay. So the trade-off clearly is spectrum efficiency versus power efficiency. All right. And there's a clear move in third generation and beyond to go towards only linear modulation. So because of that, we're going to focus almost entirely on linear modulations here in class. Right. So for today's lecture, we'll consider only unfaded channels with additive Gaussian noise. And we're going to bring fading into the picture sometime next week. We went through the basic signal space analysis, and the textbook has a lot of detail on this. You don't need to go into any more detail than what I have in the slides. It's up to you. You're welcome to do it. But there's a much more general formulation in the textbook with arbitrary number of dimensions, and I would say a lot more than you need for what we're going to do. So keep that in mind. Keep that in mind. So a basic digital modulator transmits a succession of pulses or symbols of duration t sub s seconds, and each is going to carry bits of information for a data rate of k over ts bits per second. So with groups of k bits, we have 2 to the k possible messages, and we're going to use m to denote this cardinality. So m is equal to 2 to the k. And recall the basic passband representation for the m possible messages. So we have, as usual, the in-phase component and the quadrature component. Okay, so something times the cosine of 2 pi fct, and something times the sine of 2 pi fct. Okay, and the somethings are the in-phase and the quadrature components of the passband signal, which will indicate by SI. The little I indicates the I symbol or message out of the possible capital M. That's the little I. And the big I is for the in-phase. Okay, here the big Q is for the quadrature. In the textbook, these are denoted by 1 and 2, because Professor Goldsmith has a formulation for more than 2 dimensions. So she has 1, 2, and 3, etc. So we only have 1 and 2, and we're going to call them I and Q for clarity. And these are the real and the imaginary parts, as usual, of the low-pass equivalent formulation. Now, usually we want to give all the symbols some shape, g of t, and we will see why towards the lecture. And so we're going to have some g of t, typical unit power, unit energy, I'm sorry. And so this Si of t is going to be this g of t, which carries a shape, times a coefficient Si in phase. And here we have another coefficient Si quadrature times the same shape, g of t. So in the low-pass domain, we have that the cosine and the sine become real and imaginary parts. So we have this complex number times the shape g of t. Okay? So this complex number can, of course, be represented as a vector with 2 components. The real part, or the in-phase, is the first component, and the quadrature is the second component. So for the ith possible message, we have this vector S with the in-phase and quadrature components for the corresponding index. And that's the signal constellation point corresponding to this particular message. Okay? So the collection of all the capital M constellation points defines a constellation. So here we have a picture with the in-phase and the quadrature axis, and one of the constellation points is shown. So it's a vector from the origin to the actual point, S sub I. And here we can use basic notions of Euclidean spaces, right? Such as the norm of a vector, which is the length of a vector. And in this case, it's just the square root of the squared in-phase and the squared quadrature added up. And the distance between 2 vectors is just the norm of the difference. Okay, these are, I'm sure, familiar notions. So all this formulation in its full generality applies to signals with both in-phase and quadrature components, which are complex in the low-pass domain, and whose constellation is going to lie on a plane, the complex plane. Sometimes, for simplicity, we use signals that have only in-phase components, so that they're real in the low-pass domain. And so these are vectors with just 1 dimension. And in these cases, the constellation lies on a line instead of on a plane. So we'll see some of these specifically in more detail. So that's about it for the transmitter, right? The transmitter just has to map groups of m bits into constellation points. There are capital M constellation points. So each possible group of k bits is going to map onto different points. So that's the model, that's the transmitter design. It's very simple, right? The receiver is going to be more complicated, of course. For each possible symbol that we can send, we're going to receive a version that is contaminated by noise. So we send S sub I of t, we're going to receive S sub I of t plus noise. Okay? So the receiver has to determine from this noisy observation which of the constellation points was actually sent. Okay, so that's the task of the receiver. And it's desirable to convert this received waveform into a vector. So we can use this vector notation to formulate the receiver structure. And of course, we want to do that without losing any information. So we went over this derivation 3 weeks ago. As I remember, the trick is to decompose the noise in its own passband representation and just pull terms together. And you end up with vector notation where the received vector is the sum of the transmit vector plus a noise vector. And we formulated a receiver structure that derives the received vector from the received waveform without losing information. Okay, so as you may remember, it entails, first of all, it has 2 branches. So one branch is going to treat the in-phase component, and the other branch is going to treat the quadrature component. And the trick is to multiply the signal on the upper branch by a cosine of 2 pi fct and then integrating. And this is going to filter out the quadrature component and leave only the in phase over here. And in the bottom, multiply by a sign, actually by a minus sign, we integrate out, and this is going to filter out the in phase and leave only the quadrature. And the reason for this is the orthogonality of these components, right? So remember that when we integrate here, what happens is that the quadrature component has a sign, is riding on a sign, right? So times a cosine, we have an integration that has a sine and a cosine that integrates out to 0. Remember we saw that the integration of a sine times a cosine gives us a 0. So that clears out the quadrature and leaves only the in phase on the top branch. On the bottom branch, we have that the in phase component that's riding on a cosine gets multiplied by a sine and integrated out. And all that remains is the quadrature component, which is a sine versus a sine. Okay, so that's how you discriminate the components, by taking advantage of the fact that the sine and the cosine are orthogonal, which reflects, of course, the fact that the in-phase and the quadrature components are orthogonal. Yes? Yes, very good question. What about the noise? The noise remains, right? So the noise is multiplied by a cosine here, by g, integrated out, and here we have noise prime, if you will. And we're going to see in a little bit what happens to how the noise prime relates to the noise over here. So this is a non-trivial transformation, except, and we're very lucky here, for Gaussian noise. So for Gaussian noise, as we'll see, and we'll derivate, we'll go through the derivation, the noise that comes out is the same noise that goes in. It's actually rotated, but it has the same power. But this by no means is a general principle. So the noise may be modified. But for example, if the noise is non-Gaussian, its distribution could change over here. But for Gaussian noise, it remains Gaussian, and it has the same variance. It's a very good question. So this is a property of Gaussian variables that are very symmetric, and you rotate them, they remain Gaussian. You scale them, they remain Gaussian. But for other noises, which are always sometimes encountered. In wireless, everything is Gaussian, but in wireline communication, sometimes there is impulse noise, and in photonics, they have a lot of impulse noise, have to do with photonic transitions and shot noise. And in that case, this would not be true anymore. So the noise could change a lot during the chain. Very good question. Okay, so that's how we discriminate the in-phase and the quadrature components of the signal. And actually, you just made me realize that this is somewhat incorrect, because here I've forgotten the noise. So here there should be also, in the picture, it's not only a signal that goes in, also the noise goes in. So I hope that didn't confuse you guys. That's a good point. So here there's also noise. So I'll have to correct that. Okay? But essentially, the point is to exploit the orthogonality, and in this case, embodied by the sine and the cosine. And of course, if the signal only has in-phase component, then the receiver simplifies, and there's only one of the branches. So only the top branch exists. So we can just remove the lower branch, and the quadrature noise has no effect. Now, we saw also that there is an equivalent representation of this receiver structure, which is the one here in this chart, which is the one actually used in practice. So this is how the receivers are actually built. And remember, we went through the equivalence between these two structures, right? So this is a convolution. These two boxes are convolutions by filters which are G flipped over. So it has minus T, right? So we take whatever G shape, whatever shape G has, just flip it over, and delay by the capital T. Those are these filters. And when you convolve these with the input signal, this convolution actually gives you exactly this integration, okay, times this multiplication over here. So this multiplication by G and this integration are exactly equivalent to this convolution and this sampling here. And we've also done something else here, which is instead of having an oscillator with a cosine and an oscillator with a sine, we have a single oscillator with a cosine, and then we just delay it. We shift the phase by pi over 2. And that cosine becomes a minus sign. So that's how actually actual phones work. So your phone has an oscillator, just one, that generates a cosine, and then it has a phase shifter that turns that into a sine. Okay, so you only have to have one oscillator, and you can generate a cosine and a sine. Okay, so that's how things are done, and then you have this convolution. So this is pretty much how your cell phones work in terms of the front end of the receiver, and then you have this box, which is the one we're going to study now. How you use this information to now make a good decision about what was actually sent. Okay, so this is what the smarts are. This is how you just pull out the information that you need to process. Okay. Did we see this already? Oh. Yeah, we saw this. Okay. Now we have derived the received vector R, which is the transmit vector plus a noise vector. And the receiver, so this box that says make decision, has to decide which of the constellation points was actually sent. And it has to do so in order to minimize the error probability. Okay, so we want to do the following. We want to decide for the constellation point as a by that satisfies this condition, right? The probability of this particular as S sub I having been sent, given that we observed a certain vector R, should be bigger than the probability of any other S sub j having been sent. Okay, so we want to choose or decide in favor of the constellation point that has the largest probability of having been sent, given what we observed. All right, so this is, I'm sure, reasonable to you. And to achieve this, we're going to define a set of decision regions that partition the signal space and that are disjoint. So what that means is that we want to define some decision regions such that every possible received vector, received point, belongs to one and only one of these regions. Okay, and then we're going to decide for the okay, so we'll use these to make the decisions, but the definition of the regions is the ith region contains all the received points for which the probability of that particular S sub I with the same index having been sent is bigger than for all the other points in the constellation. Okay, so that's the definition of the ith region. It's the collection of all the points for whose the ith constellation point has the largest probability of having been sent. Okay, that's Z sub I. And then if we receive a point that falls in this region, we're going to say that S sub I was the point that was sent. Okay, so maybe we can do a picture. Maybe just make up a constellation. Imagine that we have a constellation with 2 points, here and here. Which are my decision regions? Well, usually you do something like this, right? You'll draw a line here and say, okay, this upper part is the decision region for this point. This lower part is the decision region for this point, right? Assuming that the points have the same probability, this is actually optimum, right? So if your point, if you receive a vector that falls over here, you're going to say, okay, it's in this lower part of the plane, so I'm going to say that this was the point that was sent. Okay, so you can do the same thing with more complicated constellations, having more points. You can always find a set of regions that satisfy this condition. Okay, and then the receiver just decides for the constellation point whose region the received vector finds. Now, if all the points are equally probable, all the constellation points, then this is tantamount to deciding for the closest point in distance, right? Which is a very intuitive criterion. So if you receive something that's close to this point, you'll say this was the point sent. You receive something that's closest to this point, you'll say this was the point that was sent. So that's called the maximum likelihood criterion. Okay? And it is equivalent to this optimum a posteriori criterion as long as the points are equiprobable. And I believe we actually showed that rigorously. Remember that we can use Bayes rule to write down the probability that SI was sent given an observation R is equal to probability of the observation R given that SI was sent times the probability that SI was actually sent divided by the probability of the observation R. And we want to find the SI that maximizes this probability, has the largest probability. So since PR is common to all of the possibilities, doesn't play a role, right? So in other words, we want to maximize these on the left, which by equivalence is the same as maximizing these on the right. Since P of R doesn't depend on I, you can just forget about it, and we can just maximize this numerator. Now, when all the points have the same probability, 1 over m, right? There's capital M points. Then this is just 1 over m, and so it's constant, so we can also forget about it. So we can just maximize this probability, okay? Which we're going to label as capital L, and we're going to call it the likelihood function. And so we're down to maximizing this likelihood function, okay? Now, this is a random variable with the Gaussian distribution. Since the in-phase and quadrature components are independent, and they're both Gaussian, this is the product of two Gaussians, which is a complex Gaussian. So that's the probability of R given that SI was sent. It's just a Gaussian where SI is the average and N sub 0 is the variance. So this is the product of two real Gaussians, okay? It's a complex Gaussian. And this factor, again, is a constant, so it doesn't play a role in any maximization. So we can just maximize this exponential. And since the exponential function is monotonic, we can just maximize the exponent. Okay, so we're down to this, is the log likelihood function, noted little l. And remember that this is just the distance between two vectors. So it's just the distance between the vector r and the vector si. And so we want to maximize this quantity, which is negative. And so that's the same as minimizing its negative version. So, right, maximizing this is the same as minimizing its negative. So we drop the sign. And except for N sub 0, that means minimizing the distance between R and S sub I. Okay? So as long as the constellation points are equiprobable, remember that we use that. The optimum a posteriori policy, which is this one, is equivalent to this maximum likelihood policy criterion, which boils down to a minimum distance criterion. Okay. Now, if we had a case which we're not going to have, because we're always going to assume that the points are equally probable. But if they were not, then this would not be true anymore, right? This would no longer be optimum, and we would have to redraw the decision regions, right? For example, maybe we can do this example. Okay, so let's imagine that this point has 90% probability. And this point has 10% probability. Okay? So it is no longer true that we can just draw the line I had before to make the decision. Now, you guys think the line, so the line is still going to be diagonal, right? by symmetry. But you guys think it's going to be above the origin or below the origin? Below the origin, right? It's going to be somewhere like here. Because this guy has small probability. So even if you're close to this guy, chances are that this will send, right? So that's going to change the shape of decision regions. So that the criterion of choosing based on distance doesn't work anymore. But lucky for us, we're not going to have to face this problem.
Is there ever a time that's in science where do they know which one do they know is the equal probability or is it?
Yeah, the question is how is it done in natural systems, right? It's always equal probability because it improves the capacity. So there's always a penalty to pay for making the point unequally probable. So it is never done. I don't know of a single system that has something that's not equal probability. So you guys don't have to worry about this. But just just be aware that the fact that we can use distances is an artifact of the fact that that this is true, that it's the case. Okay, so I think this is a good time for a break, and then we'll start with new stuff in 15 minutes. Okay. Okay, so give me your name because you have a valid point. You know what? I'll give you your. it up. So we were here, and this is actually where we stopped 3 weeks ago. So we're getting into brand new stuff. So let's recap, okay? We've seen the structure of the transmitter, which has to take groups of k bits here, and map them into one of capital M possible constellation points, with capital M being 2 to the k. So the job of the transmitter is pretty simple. The receiver has the toughest job, right? It has to observe one of these points corrupted by noise and try to guess which was the actual point that was sent. Okay, so we've seen the structure of the receiver. We're here, these two branches in phase and quadrature. And now we started to blocks. Let's see. And we saw that under equal probability of all the points in the constellation, the a posteriori probability rule becomes equivalent to this maximum likelihood criterion, which boils down to just choosing the closest point in Euclidean distance to the one that you receive. Okay, so we justified that rigorously, and now we can start to look at the error probabilities. Okay, because since there is noise, every once in a while we're going to make an error. So we're going to say, okay, I observe this point, I look for the closest point, I say this is where was sent, that actually was the other one. That's going to happen. And we're going to now see how we can quantify this quantity, which is very important, which is the error probability. All right, so I'm going to otherwise state it, and it won't be stated. We'll consider equally probable symbols. Okay, all the points in the constellation have the same probability, 1 over capital M. Okay, so let's go over the derivation of the error probability. We're going to call it P sub E. Okay, that's the probability of error in a group of k bits, which means that the point that we chose on the constellation is not the one that was actually sent. That means that at least one of the k bits is going to be an error, possibly more than one. So that PE, we can expand it first of all using something called the law of total probability, which you may or may not have seen before. Most of you probably have. It's a basic principle in probability theory that allows us to expand the probability as long as we have a set of disjoint events. And here we have the joint event, right? We have capital M possible points, and only one is going to be sent. Only one. Okay? Not two. Only one is going to be sent. So since these events are disjoint, because only one is going to take place, we can expand their probability as a summation over these capital M points of a product of the probability of error given that the ith point was sent times the probability of that point being sent. Okay, so the sum of these products over all the possible points is going to give us exactly their probability. Okay, so this is it's called the law of total probability. So we can further expand this by noticing that the probability of error given that the ith point in the constellation was sent is the probability that the received vector R that we observe falls outside the decision region for the ith point. Okay, that's by definition when we make an error. The point, there was so much noise that the point was pushed outside of its decision region, and it fell in some other point's decision region. That's the definition of an error. So even though the ith point was sent, we decide for some other point. Okay, now since the points are equally probable, the probability of each of them being sent is just 1 over capital M. Okay, so we can just take this out of the summation. It's a constant. And we're over here. Now, the probability that the received vector R falls outside the ith decision region is equal to 1 minus the probability that it falls inside the region. Okay, the probability of something happening is 1 minus the probability of the opposite, of the converse happening, right? Of everything else happening. So we can just replace this P with 1 minus P of its converse, and expanding out the product with the 1 over M, we get this modified equation, this expression. So we're down to 1 minus 1 over M, this summation of the probabilities of R falling on each of the regions, given that the corresponding point was sent. Okay, now what's this probability? What's the probability that R falls inside the ith region, given that Si was sent? Well, it's the integration over the ith region of the PDF of R, given that Si was sent. Okay? So we have the PDF of R, given that Si was sent, and whatever falls inside the actual region, the area that falls inside the actual region, the integration of this is going to give us the probability that we fell inside that region. And the integration outside is going to give us the probability that we fell outside. Now, who is this vector R, given that Si was sent? Well, it's just Si plus noise, right? So we say that Si was sent. We have Si plus the noise. So we can replace this R given Si but by Si plus noise. And what we can do now is remove the noise from here and also from here. So we can shift the integration I'm sorry, not the noise. We can remove Si from the argument and from the integration area, right? Integration limits, if you will. So we can remove Si from here, and we get Si plus n minus Si. We get just the noise. And now we have to shift the integration by Si. Okay, so whatever region this was, we just shift it by Si. Okay, so this is the same as this. We integrate, it's the same integration except shifted in space, right? So maybe we can try to demonstrate this graphically. So let's go back to the concentration with 2 points and equal probabilities. We have these two decision regions, right? And we say we have to integrate on the ith region, okay, over here. So that means integrating over this upper part of this diagonal line, okay, if this was the point that was sent, integrating over this upper line. Now we can just shift this point to the origin and then move this curve down. You can shift the whole thing down. And now the integration is going to proceed from here up. So everything moves down. The integration doesn't change, right? It's invariant to a shift. So in this case, we can shift by Si. Go with it here. Okay? So now we get an integral that we cannot solve, but it's something we can build on. In fact, we have that the error probability is this integration and is invariant to shifts and rotation, right? Also here, we can rotate this whole thing. We take these 2 points. Imagine that there's an axis connected them. We'll rotate the 2 points, rotate the line in the middle, right? And we have an integration that's now on some other plane, but it gives a answer, right? For example, we can rotate these 2 points and put them on the axis, right? So we have 1 point here, 1 point here, and now the division is exactly on the imaginary axis. So now we integrate over this plane, and it's going to give us the same answer, right? So this is something to keep in mind, that these error probabilities, you can rotate the constellation or shift it, and the error probability is not going to change as long as everything remains equidistant. I mean, as long as the distances are compressed or expanded, it's not going to change. So in any event, this integration can only be solved numerically in general. And so the exact error probability in general, in a few cases it is available, but usually it is not available in closed form. Now, we're interested in finding closed form expressions, even if they're not exact, but they approximate, that we can work with. And so we're going to use something called the union bound to derive such expressions. So the union bound is something used very often in probability, and it states that given two events E1 and E2, the probability of their union is less or equal than the sum of the probabilities. So again, let's see if we can use a picture. Imagine we have two events. This is one event. This is another event. So the union of the events, I'm sure you all understand, is this, right? Okay, is the inclusion of both events. Now the probability of the union, let's say that this is event E1. Remember, it goes out onto the outer line here. This is event E2. It goes onto this outer line. The probability of the union of these two events is the probability of E1 plus the probability of E2 minus the probability of the intersection, right? Because remember that if we add that, the probabilities, we're counting this area twice. Okay? So to be fair, since we're counting this twice, we have to subtract it once. So that's what we have here, right? And this doesn't happen if the events are disjoint, right? If we have events that are like this, one event, another event, because there's no overlap, we can just add the probabilities. But if they're not disjoint, then we have to say probability of one plus probability of another minus the probability of the intersection. Okay? Now, since probability is always positive, this summation of three terms is guaranteed to be less or equal than the probability of E1 plus the probability of E2, right? Because this term is positive, and so its subtraction can only diminish the resulting sum. Okay? So the union bound is exactly this inequality between this term and this term, right? The union bound says the probability of the union of two events is always less or equal than the sum of the probabilities. If the events are disjoint, like these two events, then this is actually inequality. If they're not disjoint, like these two events, then it's going to be an inequality. Okay? So we'll be using this quite frequently. Now, going back to our formulation, let's define as A sub ik the event that the received point R is closer to S sub k than to S sub I, even though S sub I was actually sent. Okay? Remember, A sub ik is the event that R, what we observe after the noise, is closer to k than to I, even though we sent I. Okay? So we're going to have a problem here. So the probability that there's an error given that Si was sent is the probability of the union of these events, right? So is the union of only A sub ik's for k different from I. So if k is equal to I, then there's no error. Otherwise, there is an error. So the union of all these possible error events is the error probability given that Si was sent. Now, applying the union bound, we can express this, or we can upper bound this union as the sum of the individual probabilities of all these A sub ik. All right, for all k going from 1 to m except for I. Now, let's study each of these probabilities individually, and then we'll put them together into the summation. Okay? So the probability of A sub ik is, by definition, right, the probability that S sub k is closest to R than S sub I is close to R. So the probability that the norm of S sub k minus R is smaller than the norm of S sub I minus R, given that Si was actually sent. All right? So we know that if S sub I was sent, then R is equal to S sub I plus noise. Okay? If we send S sub I, we receive S sub I plus noise. So we can replace R here and here by S sub I plus noise. See? Here we have a nice cancellation. S sub I is cancelled out, and we get just the noise. We get minus noise, but the norm is insensitive to the sign. So we just get the noise. And on the other side, we get S sub k minus S sub I minus noise. We can just flip the signs again. And that's what we get. N plus S sub I minus S sub k. All right, so we found that the probability of this A sub ik error event, which is the probability that we confuse symbol I with symbol k, so we send symbol I, but the receiver decides for symbol k, is equal to the probability that this quantity is smaller than this quantity. So let's look at this carefully. we have that the probability of A sub ik equals the probability that the noise is strong enough to be closer to the point sk minus si than to the origin, right? Remember, this is the distance between the noise and sk minus si. This is the distance between the noise and the origin, okay? Because we can just say that this is the norm of n minus 0. So that's what I express here in English. This piece of P of A sub ik is the probability that the noise is closer to the point sk minus si than to the origin. Okay, so imagine this is the IQ plane. This is the point sk minus si. Remember, we sent si, we actually decided for sk. This is the difference. And the noise is closer to this point than to the origin. Okay? So what's the probability that this happens? Well, imagine there is a line connecting the origin with this point. All right. The noise projection on this line, so how much the noise is going to move on this line, can actually be shown very easily to be a real Gaussian random variable with variance n0 divided by 2. Okay, the noise, remember, the noise is Gaussian with variance n0 divided by 2 on the I component, n0 divided by 2 on the q component. Total variance is n0. Now, on any particular direction, the variance is n0 divided by 2, just as it is on the I and q directions. So let's denote the distance between the origin and this point sk minus I by dik. Okay, so we'll use this just to make the notation more compact. So the probability of this error event, aik, is the probability that this random variable, this Gaussian random variable, which is a noise, on this line, is larger than half this distance. All right, remember that we're trying to find the probability that the noise is closer to this point than to the origin, which means that the probability that the noise is stronger than half the distance. So you can actually go more than half the distance. Okay? So we want the probability that this Gaussian random variable with variance n0 divided by 2 is larger than dik divided by 2. So we can use the familiar Gaussian Q function to express this. And that's how it comes out. Remember that to use the Q function, we put the argument on the top, and we divide by the square root of the variance, okay, for zero mean random variables. So the probability that the Gaussian random variable is larger than some quantity is the Q function of that quantity divided by the square root of the variance. So here in this case is dik divided by 2 divided by the square root of the variance is n0 divided by 2. So we have the root of n0 divided by 2. So we have a 1/2 in the numerator. We have 1 divided by square root of 2 in the denominator. We can just clean this up. And we have q of dik divided by root of 2n0. Okay? So that's the probability of A sub ik. Okay? Now, where were we using this? Well, this was over here, right? And adding up all these probabilities is going to give us a union bound for the probability of error given that Si was sent. So we end up getting something like this. The probability that there's an error when Si is sent is upper bounded by the sum for k going from 1 to m except for I of q of dik divided by root of 2n0. Okay? And bear with me, guys. I know this part is a little heavy, but it's an important derivation. So, do you have any questions? Is any point not clear? The textbook goes into this in a lot of detail and has some nice pictures of this projection and stuff. But is there any particular question of dark? Okay. If at some point there is, please just jump in. Huh? Okay, so let's recap where we are. Okay, we're trying to find the probability, and we found the integration that we cannot solve, so we want to upper bound it in closed form. So we used the union bound to express the probability in the case of a particular Si being sent as a summation of probabilities involving the I vector and each of the other k vectors, these AIKs. And each of these guys, each of these AIKs, it ends up being a Q function. Okay, so we put them together and we find that the probability of error given that Si was sent is bounded by the sum of Q function. Okay? Now from this we have to find probability of error itself, right? So we have this. We just derived this guy over here. Now we have to add them up from I equal 1 to m times the probability of Si being sent, which is 1 over m, because these are equally probable, we said. Okay, so that's going to give us this formula. Okay, we just took this guy over here, and we plug this in here. Okay, we get a double summation. This is the outer summation. This is 1 over m, and this inner term is another summation of Q functions. Okay, we put everything together, and we have this 1 over m, outer summation, inner summation of Q functions. Okay, so that's the error probability. Remember, this is a bound, right? This is an inequality. Usually, it's not going to be an equality, but it's a useful bound. Now we can obtain a simpler, although looser bound, by using the concept of minimum distance. Okay, so we have all these DIKs between the ith and the kth point, and let's just take the minimum of them. The smallest of all these distances. There's possibly a whole bunch of them. If we have many points, we just take the smallest of the distances. We call it the min. We can plug it in here and get a nicer, simpler formula, although it's not so tight. Right, we have 1 over m some okay, so we replace dik by dmin. Now what happens is that dmin doesn't depend on k or on I, so we can come out of the summations. Okay, so we have the Q function divided by m times these summations, and now this summation goes from 1 to m except for I, right? So it's m minus 1. The summation goes from 1 to m, so it's m. We have 1 over m. Okay, so it just comes out to being, sorry, I put the m twice. So it comes down to being m minus 1 times the q of the mean over root of 2 and 0. So that's it's a more compact bound, but it's not so tight. Finally, there's another approximation that is often used. It's called the nearest neighbor approximation. And this is not a bound, notice. So this may actually be bigger than PE. So we're not guaranteed to have something, this can be actually smaller. We're not guaranteed to have an inequality. This can actually go the other way around. But it's usually very close. And it's very easy to compute. It's just this m sub d mean, which is the number of neighboring constellation points from a given one, times q of the mean over root of 2 and 0. Okay, so this m sub the mean is the number. So you take a constellation point, and you say, or you find the number of neighboring points at the minimum distance. Okay, we'll see examples. So we'll see how to compute this in actual constellations. Okay, we're almost done with this part. Just bear with me. So we have these three formulas. We have the union bound, this simplified union bound, and then we have the nearest neighbor approximation. Now, each of these involves a Q function, right? It's useful because, we can just look at the tables on the internet or use a calculator or MATLAB to compute the Q function, but it's not quite closed form. So to get closed form, we can actually approximate the Q function using this exponential. And I believe we saw this formula earlier in the course. So the Q function of z can be approximated by 1 over root of 2 pi z times this exponential of minus z squared. It's basically a Gaussian, right? And And this is pretty tight for an R to Z. So this approximation is very useful at highest n R. There's a looser version which has only the exponential part without the correction terms, which is sometimes used because it's more compact, but it's also less tight. Okay, so we'll be using sometimes one or sometimes the other. They're both, this is always bigger than this is always bigger than this. Okay, so we have two inequalities. And this first one especially is very tight for an R to Z. So at highest n R is very tight. And let's go to an example, okay? This is a constellation with 4 points on a circle. This is by far the most common constellation in actual systems. It's called QPSK, and we'll see it in more detail later or next week. It has 4 points on a circle at the same distance from the origin. So let's say we have a circle of size capital A. We have these 4 points, and you can rotate these. Remember, we can rotate the points and nothing changes. For simplicity, I'll just put them on the axis. And let's say that this A divided by root of n0 is equal to 4, right? Just for the sake of the example. So let's look at the distances, right? D1, 2. And by the way, the points are labeled as follows. This is 1, this is 2, this is 3, this is 4. Okay? So D1, 2 is equal to D2, 3, is equal to D3, 4, and to D1, 4, right? So these distances are the same by symmetry. And how much are each of them? Okay, well, this is A. This is A, right? This is a triangle, right? We have A and A. So this is A times square root of 2, right? Just a triangle. So these 4 distances are equal to square root of 2 times A, and this is the mean, right? I mean, from this point, for example, the closest points are these 2, and each of them is at square root of 2 times A, right? So this is the mean. Now, D13 is this, and D24 is this. These 2 distances are bigger. Each of them is 2A, right? And that's it. So we have 4 points and 6 distances. And we have them all here. So let's compute the union bound, right? By symmetry, we can just forget about the outer summation, right? Because for each of the points, everything looks the same. In other words, the perspective from point 1, what you see from point 1 are 3 points in certain angles. You see the same thing from each of the other points, right? You see a point in front and 2 on the angles at the same distances, right? So it's completely symmetric. All the points move the same. So the outer summation is going to give us the same answer for I1, I equal to 2, I equal to 3, I equal to 4. Okay, so we have this 1 over 4, and the summation from 1 to 4 cancel out, which is going to repeat the same stuff 4 times divided by 4. So we remain only with the inner summation. And we can pick any of the points as a reference, since they're all the same. So let's pick the first point. So we have a summation for k different from 1, so k equal to 2, 3, and 4, of q of d1k over root of 2 and 0. So we have 3 terms in the summation. First, for k equal to 2, to 3, and to 4, right? So 2 of them are symmetric. So, right, from the first point, these 2 points are symmetric, and then this one is a little more far away. So we just plug the numbers, and we find that we have twice the q of a over root of n0, plus once the q of square root of 2a divided by n0. Okay? So since we said that a over root of n0 was 4, this comes out to twice the q of 4 plus the q of, and this is square root of 2 times 4, which actually happens to be root of 32, right? You move funny, right? So it's my chalk. So we have so we have in the second q we have this, right? This times 4, right? And this is root of 2 times root of 16, right? Which is root of 34. Okay, so we can just look at the Q function tables or calculator, and this comes out to 3.1 times 10 to the minus 5. So it's a pretty small error probability, right, in this case. Now, that was for the union bound, right? Remember, this guy up here. Now, let's look at the loser simplified bound. So this one is easy, right? It just 4 minus 1 is 3 times this Q. So it's 3 times the Q of 4, which is 9.5 times 10 to the minus 5. So it's about 3 times smoother. So it's a worse bound, but it's somewhat easier to compute, right? And finally, let's look at the nearest neighborhood approximation, which is 2 times Q of 4, right? Remember the definition. Is the number of neighbors at the minimum distance times this Q function, right? So take this point. How many neighbors are at the minimum distance? These 2, right? And the same for each of the points. So we have 2 times Q of 4, which is, amazingly enough, 3.167. Look at this, right? It's exact down to the third decimal point. So this is always a very good approximation. So it's a very useful formula for this reason. It's simpler and very tight. Couple comments. Note that when there are only 2 points in the constellation, then all the bounds are equivalent. And in fact, in those cases, the bounds are exact. So the union bound actually ends up being an equality. So all these inequalities become equalities when you have only 2 points. And the reason is that you have this joint set, right? So when you have only 2 points, okay, so imagine I send this point, right? If I make an error, I can only make one possible error, right? Which is to choose this guy. Vice versa. If I send this guy, I can only make one error, which is to choose this guy. So these are disjoint events. Instead, in the example we just saw, right? Imagine I send this point 1, right? I can make errors because I can choose 2, 3, or 4, right? So then you have all these events are non-disjoint. And so we have the union bound in this case is an inequality. So it's a special case, right? When there are only 2 points, all the bounds are equivalent and they're all exact. And so for this particular constellation, you can actually derive from all of the stuff exactly, but it's the only one. Now notice also that in this case, because we only have 2 points, we're sending only 1 bit, right? We have capital M is equal to 2. Remember this relationship? 2 to the k, right? So this is 2, so k is 1, right? So we just have 1 bit. So the probability of error means that that particular bit was in error. So we just send 1 bit. So then PE, the probability of error, is equal to the probability of bit error, which is PB. Now, this is not always the case. In fact, it's only the case here, right? In general, when you have an error, it means that one of the bits can be an error, or it could be more than one, right? For example, in this case, we have 4 points, so we're sending groups of 2 bits. We can have 1 bit in error, the other bit in error, or both bits in error, right? So in general, probability of an error in the symbol or in each of the bits are going to be different, right? So we're going to use PE and PB to denote these different probabilities. And when we only have 2 points, then they're going to be always equal. Now, in general, we're going to have more than 2 points in the constellation. Usually we'll have 4, sometimes 16, even more. So then we have that PE is different from PB. Now, here we can do something clever, right? Which is carefully map the n possible groups of k bits onto constellation points to get the best possible PB for a given PE. And that's called gray mapping. So I think the best way is to do it with a baby example. So let's go back to our constellation with 4 points. Okay, so we're going to send 2 bits with 4 points. So we have 4 possible messages, right? 0, 0, 0, 1, 1, 0, and 1, 1, right? These are all the combinations of 2 bits. There's 4 of them. There's 4 points. So we have to map each of these messages into one of these 4 points. So let me give you a way of doing it, and then you guys can comment if you think it's the best way or not. Okay? Let's do this. Okay, so this is one possible way of mapping pointing to the constellation, right? Now, anybody thinks this is the best way of doing it? Except for you? Anybody else? Exactly, right? These 2 guys, right? Does everybody sees why this is better? Okay, so the point is the following, right? From here, if I make an error, chances are it's going to be with this guy or with this guy, right? Because they're closer, right? This error going here, from here to here, is harder because it needs more noise, right? So usually the noise will push you into the closest point. So you want to make sure that you make the fewest amount of errors. So in this case, you want to have just 1 bit difference, right? Which was your thinking, very good thinking, right? So now the most common errors just result in 1 bit error, right? The most rare error results in 2 bit errors, okay? So doing this is called gray mapping. So making sure that neighbors are different only by 1 bit. Now you cannot always do it, but often it is possible, and so it should always be done. Very important. So when you use gray mapping, if you assume that the errors are always going to the closest neighbors, right? So that the errors to guys that are not the closest neighbor are rare, then you can say that PB is about PE divided by log 2 of n, right? In this case, we can say that PB is PE divided by 2, right? So this approximation, in our case, log of 2 of 4 is 2. So it says that we have 2 bits. If we make an error, we just make 1 bit an error, right? So the probability is divided by 2. Okay? So that works as long as you have gray mapping, and as long as the errors always go to a closest neighbor. Okay? Usually that's the case. So it's a good approximation. Okay, let's go briefly and then we'll stop onto the most common forms of consolidation. Then we'll study them in detail next week. Let's see. Amplitude and phase. Okay, so we have amplitude and phase modulation, which embed the information into phase and or amplitude. Okay, so this is the usual passband signal in phase and quadrature. This is the low pass equivalent. We've seen this already many times. And there are 3 types of amplitude and phase modulation. The first one is PAM, which stands for pulse amplitude modulation. And this modulation embeds the information only in the amplitude. The second form, which is called PSK, phase shift king, which embeds the information only in the phase. And then there's one called QAM, quadrature amplitude modulation, which embeds information in both the amplitude and the phase. Okay? PAM, only amplitude, PSK, only phase, QAM is both. And the structures of the receiver and transmitter are the ones we've seen before. So definitely we've seen these before, right? Remember? And we haven't seen this structure, although we've talked about it, right? You take the I and Q information coefficients, give them the shape G of t, multiply one by the cosine and the other one by the sine, obtain as usual by just shifting a cosine, add them up, and that's your signal. Okay? The receiver, we have the same branches. You see the interesting parallel structure, right? We always have 2 branches, which are riding on cosines and sines. And we have G of t here, and here we have G of capital T minus t, flipped over t, flipped over G, shifted, which is going to convolve, and there's a sampler at every t seconds, right? So they're almost mirror images. Now, few comments here which are of practical nature. The receiver needs to establish synchronization on multiple levels, right? So we need first frequency, right? We have FC here, so we are creating a signal with frequency FC. The receiver is multiplied by a cosine of 2 pi FCT. So this FC better be the same FC as over here. Otherwise, we're going to have a problem. So the receiver needs to establish frequency synchronization with the transmitter. And there's a special circuit in the cell phone that actually does that. So it locks onto the frequency. Very important. You know, you have like your cell phones that you guys have operate at about 2 gigahertz, at 1.9 gigahertz. And the circuits are able to lock the frequency within a few hundred hertz of the actual frequency. So it's quite remarkable, right? How a precision that is achieved by the frequency synchronization circuitry. So out of 2 gigahertz, which is 2 times 10 to the 9, coming down to a few hundred hertz of precision. And that is done. Then the receiver also needs to establish synchronization in terms of timing because of this. This guy has to sample at the right instant. And we'll see more on that coming up. And then finally, we also need to establish synchronization in terms of phase. So whatever phase phi sub 0 this cosine has, we have to recover it over here. Okay, and have the same cosine with the same frequency and phase. We don't have to do this, but so these two are mandatory, frequency and timing. Phase is optional, but it's desirable. So if you do synchronize in phase, then the receiver is called coherent. Okay, so if this phi here is locked onto the phi sub 0 over there, then the receiver is coherent, and these are the best receivers. If they're not equal, if we don't make any effort to lock these phases, then the receiver is called non-coherent. And what happens then is that some of the in-phase information actually is gonna filter down into the quadrature realm and vice versa, because these cosines are not, the cosine and the sine, if they have different phases, don't remain orthogonal. So the separation doesn't work anymore. Some of the in-phase actually is going to end up appearing here on the Q rail. Some of the quadrature is going to appear over here. So that's called IQ imbalance, and something to be avoided. Of course, there's no problem for the PAM signals. So if you use only in-phase components, then there is no issue here. But then we use only half of the signal space. So the special circuitry of the receivers that performs all these synchronization duties, frequency, timing, and phase. And we're going to assume perfect synchronization in time and frequency throughout all our derivations. Okay, so FC is the same, and the timing is the same. And most of the time, we're going to assume also coherence. We'll talk a little bit about non-coherence, but by and large, we'll also assume coherence. Okay, let's just cover quickly these ones. MPAM. This is just a cosine, right? This MPAM has only in phase, has no quadrature, so there's no sine. We have only a cosine. And remember that the amplitude is equal to the in phase square plus the quadrature square root. Okay, so when there is no quadrature, the amplitude is just exactly to the in phase component, right? So we can just say that the ith signal is going to be the amplitude of the ith signal times g of t times the cosine. Okay. So the information is all in this amplitude. So in this case, the constellation lies on a line. Remember we said that before, right? So the q axis doesn't play any role. Everything is on the I axis. And we have all these points just at equally spaced and symmetric with respect to 0, right? We want the constellation to be symmetric with respect to 0. So we have a bunch of points spaced by 2D. And so in this case, the minimum distance is just 2D. All the points have the same, each point has two neighbors at distance 2D, except for the points at the edge have only one neighbor at distance 2D. Okay, so we can actually write the points down as follows, right? The ith point has amplitude 2I minus 1 minus m times d for I going from 1 to m. Okay? So it's not a little messy, but it works, right? So for I equal 1, this is going to give us 2 minus 1 is 1, so it's 1 minus m times d, and so on and so forth, right? So if you start with 1 going to m, you start from the left, and you'll be drawing all these points. Now, an important quantity for a constellation is the average energy of the constellation, and we call this by E sub s, energy of the, it's energy of the symbol, that's what it stands for, is the energy of the constellation. And it's always defined as 1 over m times the sum of the squared amplitudes. Okay, so in this case, each amplitude is over here, 2I minus 1 minus m times d for each of the I indexes. So this summation is actually pretty tedious, but you can actually square this guy and put it in here, add this up, and you can actually find a very nice formula. It's pretty tedious work, but at the end, it's very rewarding because you find this nice formula. It's 1/3 of m squared minus 1, m is the number of points, times d squared. And remember that 2d is the point separation. Okay? That's the average energy of the constellation lined up like this with this type of spacing. And that's a typical MPAM constellation. So the decision regions are trivial, right? We have these points equal in space. What you have to do is draw vertical lines. At halfway between each 2 points, you have a line. And the boundary between 2 lines is the decision region for that point, right? Just look at, it's a very easy partition of all the points at minimum distance from a certain point, right? Just bunch of vertical lines at the equal spacing between the points. And gray mapping is easily achieved. For example, for 4 points, this is a gray mapping, right? 0, 0, 0, 1, 1, 1, 1, 0, right? So you take any of the points, you go to a neighbor by mistake, closest neighbor, and you're going to flip only 1 bit. That's the point of gray mapping. And the receiver structure is just trivial, right? Because there is only the in phase, so we only have the upper branch, multiplied by a cosine, convolved by this g of ts minus t sample, and then we just take the point that comes out, examine it against these boundaries over here, and pick the closest point, right? That's it. It's a very easy constellation. Questions here? Is this okay, MPAM? Okay, MPSK. Now the amplitude is constant. It's A. It doesn't depend on I. It's just constant. It's just some number. And the information is in the phase. So we have a cosine. We have g of t, as usual, the shaping, times a cosine of 2 pi fct plus some phase that now is going to carry the information. Right? We can expand this, and I think we've seen before this formula, right? We have a cosine of a sum we've seen this before, right? Cosine of a plus b is equal to cosine of a times cosine of b we've seen this before. The cosine of a sum is a product of cosines minus product of sines. So we can use this to expand this cosine here into cosines of theta I and cosines of 2 pi fct, and we get the usual in phase and quadrature representations, right? This is the in phase, and this is the quadrature, and the in phase is amplitude and shape times cosine of theta I. So the in phase information is a times cosine of theta I, and the quadrature is a times sine of theta I over here. Okay, I'm excluding the shape. And how you build these constellations is by choosing phases that are uniformly spaced. Okay, so you put the points in a circle. Yeah, here it is, right? Given constellation, PSK, you just draw a circle of amplitude A, and you draw points at equally spaced angles, right? So whatever, you have capital M points, you take 2 pi divided by capital M, and that's your spacing between points, and then, times I minus 1 for I going from 1 to M, and you get you get to draw all these points at equal spacing. Now, if we take two of these points, right, we have this circle of size A. The distance between two neighboring points, you can actually do it, compute it using, again, building a triangle. And I'm not going to do it here, but you build a triangle between the origin and two of these points, and you find that the distance between 2 points is 2a times the sine of pi divided by n. So the more points you have, the smaller the distance. As you can imagine, the sine shrinks with capital N, so the distance shrinks. And since the concentration points all have the same energy, a squared, the energy of the ES, the energy of the symbol, is just a squared. And the decision regions are just separating by radials. Right? You take a radian between, dividing n into points. And so each of these pi's is a decision region for 1 point. For example, for this point here, right, this pi is pi's. This slice of pizza, if you will, is the decision region for this point. And you can use gray mapping very easily. We saw it before for 4 points, and here you have it for 8 points. So you go from any point to a closest neighbor, and only one bit is going to flip. Okay, so you make only one error. And finally, and this is the last slide, and we'll stop here. When we have MQAM, we have information in both the amplitude and the phase. So here, A sub I has information, and theta sub I has information. So we just put together the two different cases that we saw before. And this is the most general form of constellation, and is more efficient than PAM and PSK. It is superior to both. The energies of the points are AI squared, and so you can compute the energy of the symbol as usual. In this case, it's not so trivial, so I'm not going to give you a general formula. You can work it out for specific constellations. It's kind of tedious, but just algebra. There is a very popular form of QAM, which is square QAM, which is built by taking two PAMs and putting them in quadrature, right? So building like a Cartesian product. So in this case, you take two PAMs with 4 points. You multiply them out in Cartesian, and you get 16 points. Right? So this constellation can be built by taking this guy with 4 points, and it's perpendicular version with 4 points, and you do a Cartesian product, and you get 16 points. You can do that with any of these PAMs, and you build a square QAM. And an inconvenience is that gray mapping is not always possible. Okay? But you can get pretty close. You can always try to map so that you make the smallest amount of errors when you go from one neighbor to the next neighbor. And we're going to stop here, okay? And pick it up next week. And before going, connect your midterms, okay?